very much. It's a great honor to be associated with the name of Felix Klein. He will come up in the slides other than the title. Okay. And so the main question, old style, is sort of, can we parameterize all, and then you take your favorite objects. I will take algebraic varieties, but some people take sheaves or morphism in a natural way. But the new style, and so these stacky people are behind it, but in fact it was very much implicit before. So what is a good family of algebraic varieties? And can we describe all the good families in some optimal manner? So these are the main topics I would like to address in this lecture for at least some classes of algebraic varieties. Now, this is the plan of the lectures. There will be 6 lectures, and there are the 6 topics. And I arranged the lectures that they're almost completely independent of each other. And so the consequence of this that there will not be something like a coherent proof. So it's not that 10 days from now I can put down my chalk and I told you everything. But I have no chalk, and so I sort of try to emphasize some of the main topics that go into this and that can stand on their own, and I think are interesting in their own right. And so then so hopefully after the lectures you can actually fill in all the gaps, or if not, you can read these books that are here at the bottom. Are they in the library or? No. Yes. Yes. Most of them. Yeah. Okay, good. And so today will be a very introductory to a lecture doing history and examples as from Riemann to Mumford. So if you want to hear new results, you should come back tomorrow. So if you leave now, I have really no objections. So then we'll start the first lecture. Okay, and so the first moduli problem that the people looked at were the hypersurfaces, or so the fixed degree. You fix your Pn and your degree, and then you can write down any hypersurface by an equation, sum of ai xi equals 0, and this can be parameterized by their coefficient. So we are interested in the hypersurface side, so not the equation. So if I multiply it by a constant, we get the same hypersurface. So that means the hypersurfaces of degree d in Pn, they naturally form a projective space of dimension n plus d choose n minus 1. Now the advantage of this description is in some sense is the ideal moduli problem. This works over any field. So the point of the projective space automatically know which hypersurfaces can be defined over that field. And now with hypersurfaces with multiple components here, we count components, so not just the underlying things. Now, and there is a similar description for the hypersurface sections of any variety. Okay? Now, on the other hand, maybe this is not exactly what you want to do. That if hypersurface is obtained from another hypersurface by linear coordinate change, then maybe I don't want to distinguish these two. And so in some sense, when we are doing geometry, then the interesting would be to understand when two hypersurfaces are isomorphic, how to describe the isomorphism classes of hypersurfaces. Now, and so Then of course you can ask this two-way. You can ask whether two hypersurfaces can be turned into each other by a linear change of coordinate. That's sort of the simplest. But you might be interested in just abstract isomorphism. And now, so luckily, except in a few cases, these two are the same. So for Pn, the hypersurface is just a set of points. So then the abstract isomorphism becomes only the number of points and their locations. And then in dimension 2, but there's well-known exception of elliptic curves that can be isomorphic differently. And then there's another interesting exception that these are degree 4 surfaces in P3 that can be isomorphic in a non-trivial way. So just to see an example where this can happen, and this is more or less an aside, is the determinantal example. And so we start with Pn cross Pn, and then you take the intersection of n plus 1 hypersurfaces of by degree 1, 1. Okay? And so then these are the equations of these hypersurfaces. Okay, so I don't know how to get it. Okay, here's the line. Yeah, okay. And now you can project it onto one coordinate or another coordinate. If you project it on one coordinate, then there is this determinant, a sum over where the I, so is the J and K are the remaining matrix indices, whereas here the I and K are the matrix indices. These are the projections. And you see, because of the summation and taking determinants, these two equations don't have too much to do with each other, but they obviously define birational hypersurfaces. Now, and for n equals 3, in fact, they define isomorphic surfaces, an abstract isomorphism between them, but usually cannot be obtained by linear change of coordinates. In fact, also proved that there isn't even a birational map usually from P3 to P3 that carries one hypersurface together. But so this is basically the only big class of the exceptions where these two notions of isomorphism, they are different. Okay, and so that means that aside from these few cases, we should really study hypersurfaces of degree D, mod linear changes of coordinates. Now the point is that this is a horrible space. Okay, let's just see how horrible it is. And so even if you know nothing about this, we can say something about the closure of a subset. And so let's assume that I have a family of hypersurfaces, so depending on this parameter t. And if xt is in U for t non-zero, then the central fiber should be inside the closure of U. Okay, and so let's start with this. Let's start with sort of NEF. And then I just have the transformation. I multiply the last few coordinates by t. Now, as long as t is non-zero, there's just a linear coordinate change. So that means for t non-zero, these are all isomorphic to each other. But when t is 0, then I get this. Okay? And so that means that this hypersurface is contained in the closure of the point given by this hypersurface. Okay. So that means this is a non-closed point. There is one exception that, so if you look at degree D hypersurface in Pn, then there's one closed point, which is the default hypersurface. Okay? And so, okay, so you agree this is not a very interesting space, but you might, well, or maybe it's way too interesting for me. Yeah? And so, but then of course, maybe this is okay. I mean, let's say, as I say, let's exclude this. But again, we can't go too far. For instance, if we want to look at only reduced hypersurfaces, then the similar arguments that the only closed points are the two variable ones, which is just sort of the different hyperplanes, in fact, sort of in a pencil. Then you say, okay, these are not normal. They're the only closed points are the ones that depend on three variables and the cones. Now, these are, of course, they are cones with some very large singular set. And say, okay, let's say that you want things that are not cones and have only isolated singularities. Now here, I have only some sporadic examples, but here is an example where one such hypersurface is contained in the closure of an other. So somehow just trying to get down, these are really very, you would think that hypersurfaces with isolated singularities are and non-cones, they should be sort of as mild as you can get before reaching smoothness, but it's still not enough to get some reasonable moduli space. Okay, and so therefore hypersurfaces, sort of an answer was given by Hilbert and Mumford. They say, well, it was implicit in Hilbert, very made explicit by Mumford, that there's a notion of stability. I don't want to get into it now. You hopefully have seen this. And then the moduli of the stable hypersurfaces, that's something as nice as possible. It's a nearly smooth algebraic variety, but it's not compact. To compactify it, you get a semi-stable one. This is less nice, but compact. Now, the good property is that smooth hypersurfaces, they are all stable. Maybe the degree is at least 3 or something. Anyway. Now, sort of the bad properties are, well, one is it is very hard to know what is stable. So I think exactly for degree 4 in P3, I believe Shah worked out. It's a very complicated list, what singularities are allowed, what not. It is pretty hard to use. But other than that, it is very hard to decide whether hypersurface is stable or not, or is semi-stable or not. And then the other problem is that the point of this space, a semi-stable point, corresponds to lots of non-isomorphic hypersurfaces. And in some sense, there's an optimal way of choosing one, but it's not exactly built right into this. So that means that it has some compactification issues. The boundary is not as nice as one would like. Then the other problem of this is that it sort of misses some natural smooth degenerations of hypersurfaces. And so that I think it was more in his master's thesis, wrote down this series of degenerations of hypersurfaces. So you start with these two equations, one degree is a multiple of the other, and you write down this equation. Then when t is non-zero, then you can use this to eliminate z, and you get just g to the e minus this. So these are nice hypersurfaces. But when t is 0, then what you have not a hypersurface, but a degree e cover of the g hypersurface ramified along f. Okay, and so clearly some natural smooth limits like this, there should be in our moduli space of hypersurface. Now, you see that these examples, it's very important that the degree has two factors, like d times e. And we don't know any prime degree examples. Atem and Schreier proved there are no such for degree 5 and 7. For 3, it has been done long ago, most likely in some paper of Fuji. Yeah? And there's there's an interesting question about plane curves. So when can you have smooth generations of plane curves that are not planar? So actually, this is a very tricky question, and there's a very interesting paper by the Fleming and Stapleton that agree that studied the degree 5 case. It's a very nice, it's a very nice conjecture that's there. Okay. Now, and so again, this slide is an aside. It is just a sort of small warning that it can really matter exactly how you formulate a moduli problem. And so I am looking at n+1 points in the affine line up to translation. Okay, so what can be simpler than that? But now I want to look at the subset that's even special when at least n of the points coincide. Okay? And now there are sort of two ways of doing this. You can just say that n points should coincide, or you introduce another point q, and you say that n of the points should be equal to this q. Now, you know, if you have at least 3 points and 2 coincide, it can happen only one way. So that means that it uniquely determines that point q. But these do not have isomorphic moduli spaces, these two. So I claim that the one moduli space where I do not specify the point q, then the moduli space is isomorphic to C. No, when I specify the point, it's isomorphic to C. When I do not specify the point, that the natural moduli space is a cuspidal curve. And so, let's see. So if I have n+1 points and q, I can just take the sum. Of course, almost all of them are 0. There is one difference, how different is from q. And so then this gives me the isomorph. But if I just say that is the n-fold point, let's say it's at t, then my equation can be written like that. So that means that the coefficient, it will be some constant times t to the I, but you see they start at 2. Yeah, so exactly the linear coefficient. And so then the moduli space is the image of this map, so that's a cuspidal curve. Okay? And so now you might say, well, this is who looks at an n+1 points up to translations, and maybe not, but for instance, the higher that I mentioned the way it comes out, that if you look at this singularity, then this deformation is trivial to first order, but if you do the natural resolution, that is a non-trivial deformation. And so it can happen that sort of some deformation is trivial, but the resolution is not. So there are some sort of subtleties that you just have to keep your mind on. Any questions? And so these pictures, I suppose you all know, they come from Harry Hauser.
In which sense the actual surface polystable in the GIT construction is not good? You were saying that
it's not
good in the sense you were saying that when you take the semi-stable ones,
yes,
there are a lot of hypersurfaces that represent. There is a special one, but you said that is not good.
Well, and so for instance, you can make a family actually of them where the fibers are those, yeah. So that's one problem. Okay, so then let's continue. Now let's go back to some history. So the moduli of curves, the analytic theory started with Riemann theory der Adelsfunktionen. who just says that Riemann surfaces of genus G depend on 3G minus 3 parameters. That is a fairly easy constant, and count is local. And now then, that's sort of these spaces, these moduli spaces, they are studied by the monumental work of Fricke and Klein. It appeared over several years, several volumes. And so they construct what is now called the Teichmüller space. And so they show it exists and it is contractible. I will say something more about it in the next slide. Now the next main step was Siegel, 1935, who constructs AG, the moduli of abelian varieties. And the Siegel paper has a very modern feel, so it reads like a modern paper, whereas the previous ones are well, it's not just that they are in German, but I think that even for German readers, that's clearly not what we have now. Okay, there is also here the first red herring of the theory, and so I think these translations are sort of not optimal. And then I don't know what red herring is in Chinese, but so maybe someone can tell, or some other exotic languages. So you are free to come out here and sort of put there in Chinese if someone knows it. And so the problem is that if you look at Fricke and Klein, then they say that it's what's now called Teichmüller space. These are the discrete co-compact representations of the fundamental group in PGL2R. And so modulo conjugation. Now, this is visibly a real space. There is no complex structure on it. And then look at it, PGL2R does not have a complex structure. I mean, it has three real dimensions. And so, because of that, in Fricke and Klein, the complex structure is really not discussed. There are a few examples that sort of a very complex structure comes up, but there's no indication there that there's a natural complex structure on TG, and it should exist. And this really seemed to have derailed people for something like 50 years until Teichmüller came. So yeah, and so this is to some extent similar. That it's sort of really hard to understand if you look at sort of the Wade book on Kähler manifolds that it shows that the HPQ, they're very real analytically. But somehow he missed that the filtration is very complex analytically, which is so much nicer. Okay? And so that so it happens sometimes that the people do something and it is misleading. Okay, and so then the big step came with Teichmüller, who worked out the complete theory of the G, the complex structure, and the functorial aspect. But the moduli of curves, that's a quotient of it, yeah. And it was not clear what kind of a space that is. So in the first explicit claim that it should be an algebraic variety is in Bayes' Murbach seminar talk. But it was an open question. Now, if you have some time, I can really recommend looking at Grothendieck's talks at the Cartans seminar about the space TG. So this is Grothendieck before he became Grothendieck. And so it's a very awkward presentation. So he looks at this deformation theory where the fibers are algebraic curves. So these are fiber-wise projective, but it's holomorphic in this direction. It's a very unnatural setup. And there are no schemes, no nothing. It's just, it's hard to imagine that basically next year he started writing EGA. Yeah. And then there's a lot more of the history in this paper by Acamponi, Papadopoulos. It's an archive. It's very interesting. Okay. Now, then the algebraic theory, which we will come back to this more later. It started with Cayley, a new analytic representation of curves in space. There are two papers with exactly the same titles, not even 1 and 2, it's just exactly the same title. Okay, so that seems to have been the way he has been doing things. And so he says that if you have a curve in space, then you associate a set of all lines that meet C. And now the advantage of it, that the set of all lines is a hypersurface in the Grassmannian. And we know how to deal with hypersurfaces. Yes, so hypersurfaces are basically just linear spaces. Especially here, this Grassmannian is just a quadric. So it is really very easy. And then over time, the general theory was worked out by Van der Waard and Chow, and it is prominent in the Hodge video. And so then, on the geometric invariant theory side, there was Hilbert paper, the finite generation of rings of invariance, which to us, if we see a finitely generated ring, of course, the first thing we do is take its branch. But it seemed that for something like 50 years, no one did that. That it just did not occur to them, let's take the approach, what happens. And so maybe one problem was that it was not, that these were not generated in degree 1. And so they maybe did not like this. I don't know why. Sometimes when you look back, it's really utterly mysterious why people didn't do something that's completely natural to us. But they okay, now, yes, then another interesting paper is Severi about, so we say that he proved that MG, the moduli curve of genal G, this is unirational for G at most 10. Now, and then I looked at this paper, and it's really not clear whether he thinks that MG exists or not. Yeah? So it's interesting that he calls this not a varieties, but a mannigfaltigkeit. Now, because Riemann used the word mannigfaltigkeit, and so it's possible that sort of he just sort of followed little Riemann because that was popular. But we might ask, well, how do you prove that something that doesn't exist is unirational? But that's actually not hard. He just say that there's a family over some rational variety that gives almost all curves of a fixed genus. And so then this rational family, this sort of maps dominantly onto it. Whether it exists or not, so there is not a major issue from this point of view. Then the Bay and Matsusaka, they looked at the field of definition, field of moduli. So from the modern point of view, if you have the moduli of curves, then it should be defined over Z. So if I have a curve, then I get a point that corresponds to it on that scheme, and so it has a residue field. Yeah. But the point is, you can construct this residue field without constructing this moduli space. So somehow that was their sort of first step to try to understand the scheme. And there should be a residue field, so there can be actually write this down. Okay, and now then sort of the next disaster that happened was done by Satake, who was compactifying the moduli of billion varieties by just these lower dimensional moduli spaces. And so the boundary of AG, there's AG minus 1, and so on. And that was extended by Bailey and Borel. Now, why do I say this was a disaster? Because over the boundary of AG bar, the natural objects, according to Satake, are lower dimensional abelian varieties. So clearly there cannot be families over here. There is no family where, say, an abelian variety of dimension 3 is a general fiber and dimension 2 is a special fiber. And so, because of that, I think people really gave up on the possibility that there is a compactification over which there exists a nice universal. Now, luckily here we didn't have to wait long, one for then, and the link came soon, but so the first compactification of AG that has a natural modular interpretation was done by Alexeyev much later. So for okay. And now then sort of another problem came with GIT, okay? And so, so Mumford constructed the first MG, and then MG bar, it took longer by GIT. Actually, it was really not obvious. And so Gieseker constructed the moduli of canonical models of surfaces, and Fiebig extended these to higher dimensions. Now, but I think this was another red herring. And the other problem was that Mumford and these others, they were too strong technically. And so GIT is an essentially linear theory. Yeah? And so it sort of works very well for linear objects, like sheaves. You know, sheaves are basically linear objects, and their GIT works excellent. But algebraic varieties are nonlinear objects. Now, abelian varieties, they are basically linear objects, and because of the curved Jacobian and correspondence, you can think of curves as linear objects, but in higher dimensions, these don't seem to exist. Now, the first hint that sort of GIT will not work for surfaces was in Mumford studying the asymptotic stability of singularities. And so Mumford asked himself the question, so he could prove that, you know, that if some singularity exists on a variety, then it cannot be stable or semi-stable. So he says, okay, I start with a surface and take, say, example canonical class. I take higher and higher embeddings, and I say which kind of singularities will it happen that it will not be stable eventually, or that will be stable eventually, or at least the singularity does not rule out instability. And he came up with some fairly random looking class. So somebody did not seem to make sense. The definitive negative answer was done by Wang and Xu, who proved that if you do the GIT compactification of the moduli of surfaces with higher and higher embedding, then with each embedding, you will get a different compactification. And so not like with curves, where you have the 5 canonical embedding. After that, you get the same compactification. For surfaces, you get a different compactification. And in fact, this happens already over hypersurfaces. I think something like, I think maybe I worked out an example, hypersurfaces of degree 19, or like the surfaces of degree 19, if you just follow this, you get sort of different compactification. So that's sort of unpleasant, then think that the GIT works well on the inside, but not on the compactification. Okay, any questions?
Is the Cayley approach used in modern times? The one.
Well, if you come to my lecture 5, then there will be Cayley there. Okay. Okay. And so, yeah, maybe I have time for this. So let's see what happens with sort of genus 2 curves. Yeah. So these are smooth projective curves. Now there's a structure theorem that they have a unique map to E1, a degree 2 cover that ramify at 6 points. So they have an equation z squared equals this homogeneous degree 6 polynomial. And so the curve is smooth as long as there are no multiple roots. So that means that for M2, which is the open part, you can just say 6 point in P1 mod PGL2, or the 6 symmetric part of P1 minus the diagonals mod PGL2. And this is a completely reasonable space, and this is the right space, and this is completely. But sort of how to compactify it? Well, some roots will come together. Now, so I just worked out an example. For instance, how to do there's a fourfold root. Yeah, so t equals 0, this has a fourfold root. Okay, then we make this coordinate change, x equals tx prime, and divide by t to 4, then I get this. And suddenly, but there's a double root here when t equals 0, but the fourfold root vanished. Okay, so that's nice. So we don't have to worry about fourfold root. And then now with triple root, again we can do something. So after base change, you have to do this t squared here. So again, I make this substitution and divide by this. I get this, which means that I have just here 2 triple roots. So in some sense, you should sort of worry about this. That sort of somehow normally you would think that if there are two triple roots, that's worse than having only 1 triple root. Yeah? But at least it's unique. But actually, this is the fairly general problem with the semi-stable object. So this is the closed point, the canonical point that's in the boundary, but it's worse than all the others. So somehow GIT on the boundary tends to pick up the most singular object. So it is also not particularly good, but at least this is something that's unique. And so then we see that the GIT compactification is that the point. So there is one point when there are two triple roots, the unit points. Otherwise, at most double roots. Now, what are the corresponding curve? Well, this is rational with 2 cusps. But at most double roots, then they're almost all irreducible with one exception. So this is reducible. So if you like your curves reducible, which the classical authors really like, someone did not think that reducible curves should be considered as one object, except for conics. Yeah, I think the conics on these of 2 lines they were happy with, but not otherwise. Then we contract one component, and I get a triple point, which is like the 3 coordinate axis. So it doesn't matter which component we get, the 2 curves are isomorphic. But yeah, and so from the old style, this is the end of the story. We have the points in the space, and we know which curves correspond to it, and they look just fine. But in fact, this is a very unpleasant compactification if you want to look at families. I mean, the worst thing happens really at this point, that you look at the local deformation spaces. So the parameters are u, v, s, and t. But when u equals v0, then I have one triple point, the other three different roots, and now then you say this is not allowed, yeah, so we replace this with a triple root over here. And so that means that we have a four-dimensional local deformation space, and so the two planes of it ruled out except the point where the two planes are. Okay, so this is not some nice algebraic variety that we can handle. It's a constructible set. And now there are also some stacky problems here because we had to decide which curve to contract. And so there are two families which have exactly the same fibers, I mean isomorphic, but the two families themselves are not isomorphic. Which is again something, I mean, and it happens locally. And so globally we know there can be monodromy or something like that, but so locally this is not nice. Okay, and so then it took the combined efforts of the linear Mumford, really two of the greatest algebraic geometers at the time, to fix this problem. Okay, and so says if there are at most double roots, we keep these. If the curve is reducible, we keep it is. We don't do anything. And now, then if there are z squared equals x cubed pi cubed, so what do we do here? Let's see. And so what did we have originally? So if we think about it, here's a central fiber, and there are, okay, so this corresponds to sort of two triple roots, okay? And now they say, well, let's just blow up these points. Okay, so then these come in differently. And then you say that we just contract this. So we have an A1 singularity, so then we get a reducible curve, and sort of they come in like this. Okay? And then if you take the double cover, well, then of course you have to ramify here, here, and here, but on a P1 you need to ramify 4 points, so then you need to ramify here. And then the same here, so that means that you end up with two elliptic curves meeting at just 1 point transversally. So this is their answer. And now, so the y is this problem for us. So basically, what we do, we blow up this point and then we contract these two. So then you blow up the point, you get a P1, but when you contract this elliptic curve, it becomes a 2 plus P1. P1, but then you don't see the elliptic curves anymore. Okay. And so then you can go on to the higher dimensional case. And so I say that at the boundary we should have projective connected reduced curves such that they have a local property and they have a global property. The local property is that they have adverse nodes, at least locally, analytically adverse nodes. And the global property is that omega c is ample. And so if you look at maybe GIT, then it approaches this, that the automorphism group of the curve is finite, which is equivalent to this, but it's really the wrong way of doing this. Now from GIT point of view, that's very natural to say, because it by the action of this large group. So from GIT point of view, the finite automorphism jumps out as the natural condition. I mean, really, is ampleness of omega c is the right thing. And so what's omega c? I believe this is an audience of most algebraic geometers, and so you know what omega c is. But in case there are some laymen came in who nonetheless know what Poincare residue map is, then here is the data. Okay, so let's see, what's next? Oh yes, so then in higher dimensions, here's some basic questions. So one is, what are the correct analogs of smooth projective curves of genus at least 2? Okay, so that means that what are the objects in the interior of the modular space. And then the next question is, what are the correct analogues of stable curves? So what should appear at the boundary of the modular space? And we will see it is easier to make it work for the open part, as we have seen with geometric invariant theory this was done. But it will be harder to make it work for what happens at the boundary. Actually, I'm seeing faster than I expected. Okay, so any questions? This is almost my last slide, so this is a good time for that. Well, if there are no questions, I have one more slide, which is a homework. And so the torus is the third best known algebraic surface. So people know the plane, people know the sphere, and I really think for laymen the torus is the third best known. Do you know what the torus is? As an algebraic surface. So the homework is due before tomorrow's lecture. Marco will collect them. So we will grade them.